Okay, this unit is a continuation of the unit that we were working on prior to spring break. We did everything except for graph that, rational functions. So what we have are rational functions, which are basically fractions. So we're looking at fractions. So you can see that this P of X, right, is a could be anything. It could be a binomial, trinomial, anything like that, as well as Q of X could be a binomial, trinomial. And we're actually doing the division of those. So we got to get ready to graph these. So where the denominator is equal to 0 and is undefined, so the denominator of a rational function consists of x, which is the denominator cannot be equal to 0. So that is the denominator. So the denominator is cannot equal 0. That's where it's undefined. I can't say it doesn't equal 0, right? But the graph won't have that on there. All right. So the domain of this function, we're going to kind of find what is not in the domain of this function, because whatever makes the denominator equal to 0 will not be in the domain of this function. So we're going to set the domain equal to 0 to find our intervals for this, because it's everywhere where it could be, but where it is not undefined. The other thing, let's do that before we do the other thing. So if we look at this one, our denominator we're going to set equal to 0, so that means we need to factor it to solve it. So it's going to be x plus 4 and plus 5. 4 plus 5 multiplies and make 4 plus 5 add up to make 9, but they multiply to make 20. So 4 and 5. So if I solve this, that means x would be equal to -4. So that means I cannot have a -4 for x, because that would make the denominator 0, as well as x would be equal to -5. So if I had -5 as x, that would also make the denominator equal to 0. So let's go ahead and do our interval notation for this. So we're starting at -infinity, right? And we're talking about domains, so we're talking about x values from -infinity to -5. And then we have to jump over -5, and we got to put it together starting at -5, or close to -5 really is what it is, and go to -4. We have to jump -4 and go out to infinity. So that would be the domain of this function in interval notation. Oh, there's a union here. Got my union. There's a union there. So in set notation, remember that's that fancy bracket, x with the bar. And then in set notation, x is everything real, so it's all real except x equaling -5 and -4. Okay. Let's look at this next one, right? This one, we need to be able to factor that denominator. So we're really worried about, because all I'm finding is domain. We'll take care of the numerator stuff later. So we have two numbers. We have x plus 3, x minus 1. Okay, for interval notation, the two things I cannot have. X cannot be equal to -3 and -1. So if I solve it, I get -3 and I get +1. So we can start at infinity and go to -1. No, that's +1. This is -3. So we can go to -3. Put it together with 3 to 1. And then put the last part together to go from 3. We got to union that to go from 3 to infinity. And that would be your domain. Okay, set notation. Oh, fancy bracket, x bar, x equals double bar r, everything except. Okay, what's going to make this equal to 0 down here is going to be -3 and 1. And then you close it with your bracket. All right, that wasn't really new information. We kind of did that in the last unit. So the thing that is new, so these are vertical asymptotes. We just talked about that. The denominator is equal to 0. And that's where your vertical asymptote will be. Horizontal asymptotes. So horizontal asymptotes, we have 3 choices for horizontal asymptotes, and it's based on what you are given in the problem. So the numerator on top, we're talking about the degree also, right? In this, well, we're talking about the degree, which is the exponent on each one of these. So the numerator's exponent, in this case, is 1, which is less than the denominator's exponent right here, which is 2. In that case, our horizontal asymptote is always going to be equal to 0, so y equals 0. And this one, where they are equal to each other, right? So this one has an exponent of 1, this one has an exponent of 1. It's a ratio of the leading coefficients. So it's a ratio of LCs. Okay, in this case, where it's going to be A over B. Let's look at this example. Exponent is 1, exponent is 1. They are equal. So it's going to be 3 over 5. And that is going to be the horizontal asymptote. Y is equal to 3/5. Now, if the numerator is larger than the denominator, see the degree here is 2, the degree here is 1, there is no horizontal asymptote. No horizontal asymptote in that case. So moving down the page, oops. Okay, talked about what holes are. Well, we didn't talk about what holes are, but that's what we need to talk about. That's where something cancels out. Something that's common factor cancels out. It will make a hole. After you find the x value of that hole, so for example, you factored out x minus a, right? Then you plug in the value after canceling out and get your y value for that. So the hole is going to be at a point. In this case, it's going to be at a, because a is negative here. We set that equal to 0, comma, and then we're going to take this a and put it back into the equation and solve, and you'll get some number. And I will show an example of that in the next video. Okay, x to the 5, we just talked about that. Simplify the numerator and equal it to 0. And you find your x-intercepts that way. And the y-intercepts, well, the y-intercept is when we make x equal to 0. So if x is equal to 0, that means all your x terms will go away. And you're usually just left with 2 things. So in this case, it's going to be c over d. C over d will bear where it intercepts. All right, so I'm going to do a video and do examples in the next video.